Okay, so now we begin with lecture 26 and continue with the discussions on sedimentary rocks. And last lecture we talked about physical weathering processes involving thermal effects using ice wedging, pressure, the pressure release and salt deposition as some of the main causes. There are numerous other causes, but we restrict ourselves to what is the dominant processes. And now we come to something called, and we understood one thing, that if we have a rock and we break it apart, what we do essentially is increase the surface area, decrease the size, of course, that's very simple, decrease the size, and therefore increase the surface area of the same mass of the material. So now what happens when you reduce the surface area, you expose it to the atmosphere. And that's where the real play starts. And we will talk about it later before we proceed further. Just a moment, please. Yeah. So basically, the first thing that happens is most of the reactions would occur at about 25 degrees centigrade and 1 bar atmospheric pressure. And many of these reactions will involve the atmosphere, which contains H2O. The atmosphere also contains CO2. While these are the two important things, the other important thing is oxygen. So we will not go into the great details of it, but what you can understand that the reactions are essentially, the chemical reactions involve pH and EH conditions of the water. This you know what is pH, the hydrogen log of minus H plus, and EH, which is the oxidation ion potential. So most of these reactions that occur involve hydrogen ion and oxygen. We will only enumerate a very little part of it. But the most important thing is, in atmosphere, also you will see if you go on the ground, if you walk on the ground in India, for example, you are walking on a certain green material. Now they have their time, and they will when they grow old, they will of course decompose. And what produces humic acid. So what happens is the water that is there, or the water when it falls from the sky and from the clouds and mix it up with groundwater, and then it starts to react. This water is slightly acidic. The most water, continental waters, if I would say, have a pH between, most continental waters have a pH between 6 and 7. Most continental waters have a pH between 6 and 7. They are mildly acidic. Whereas, if you take the ocean floor, the pH of the ocean water is 8.1. which means slightly alkaline. Now what happens is, so when the continental waters like the river water, etc., when they go into the sea, with the value of, say, if you take an average of 6.5 and go into the sea, which is alkaline, there is a large change in the pH conditions. And this creates tremendous amount of reactions, change in the method of reactions, etc. So the environment, the chemical environment of the ocean water and the chemical environment of the continental waters, they're completely different. And their interface is another problem. While the ocean water is slightly saline, the continental waters are not so saline. So while the ocean water is slightly alkaline and also has a lot of salt, quite a considerable amount of soil, continental waters, unless they are special waters, they are mostly slightly acidic and much less saline. Although there are some places, like say for example mining areas, where they mine for vanadium, for example, there the pH of the water in those areas is very, very low and goes down to 4 pH or even 3 pH. They are very acidic waters. But generally continent waters are only mildly acidic. Why acidic? Because it is this H2O plus CO2. This produces H2CO3, a carbonic acid. That's the first thing. So you must have heard about acid rains or something like that. These are all slightly acidic. This is carbonic, H2CO3. And then when you have H2CO3, it can break up into H plus CO3, HCO3 minus plus H plus. So hydrogen atom. And then you have CO3 2 minus plus 2H plus. So what happens, you can see, they can dissociate into different forms, H2CO3. So a water would involve H2CO3, HCO3 minus, CO3 minus, and the concentration of the atomics of the species of HCO3, they vary from ocean basins to continental waters. I'm not going into the details. It is not necessary at this point of time. Similarly, if you remember, so you have some sort of an acidic environment in the continental waters, where you have most of the rocks. Remember, the rocks that you have in the ocean water, they are underwater. So, but the rocks that are there on the Earth's surface are mostly exposed to the atmosphere. So the atmosphere is slightly acidic because of the presence of H2CO3. And you have acidic water. Similarly, now when this water reacts, say for example, you know Si, silicon, and aluminium. These are two of the most important elements that occur in the Earth's crust. Silicon and aluminium. And as you know from my earlier lecture, these are network forming polymers. SiO4 minus, ALO5 minus, etc. All these are network forming. So if you can break down silicon and aluminium, you're chemically breaking down the minerals. So here, chemical weathering essentially involves the processes that rocks, which are composed of minerals, how they react with the atmosphere in terms of EH and pH conditions. And because of this, different elements generate different elements of speciation. We will not go into the details, but say for example, H2O reacts with SiO2 to produce H4SiO4. So that is it, orthosilicic acid, H4SiO4. And H4SiO4 splits up into H3SiO4 minus plus H plus, and then you have H2SiO4 2 minus plus 2H plus. So these are the species of the silicon atoms. So if you take the silicon atoms, they have three types of species: orthosilicic acid, H3SiO4, and H2SiO4 2 minus. It's a build-up. The silicon is held up in all these three types of species. Similarly, if you take aluminium, the species that there are of aluminium is Al, the most important is AlOH whole twice. That's the most important thing. This mineral is called gibbsite. And then you have AlOH plus, OH2 plus, and then AlOH minus, AlOH2 plus, OH4. These are the species of aluminium that are stable at 25 degrees centigrade per atmosphere. They are stable, but the stability changes as a function of pH conditions in the water. So aluminium is AlOH2 plus, AlOH2 1 plus, AlOH4 1 minus, and AlOH whole thrice, which is gibbsite. And so these are the species of aluminium that are formed at different pH conditions of the water. And this is for silicon, where you produce orthosilicic acid and then H2SiO4 and H2SiO4 2 minus. So all your silicon is carried in these species, all your aluminium is characterized in this species, and all your silicon is characterized in this species, in this slightly acidic water. Remember, if we can dissolve the rock, the silicon and the aluminium, the whole structure of the rock essentially crumbles. So now what we do is, I will show you, this can be done thermodynamically, but I really don't have time, although I would love to do it. So I draw a diagram. So this diagram, solubility decrease, this diagram is the solubility of aluminium silicon in parts per million. Parts per million means 1 in 10 to the power 6. And if you do that, I'm not giving you the scale because then it's slightly difficult. So what we have essentially these are the solubility curves of aluminium and silicon. This value here is the pH of seawater, 8.1. And most of the continental waters are restricted to between 6 to 7. Now, I have not given you the values, but you have to take my words as they're true. The solubility of both silicon and aluminium, solubility of both silicon and aluminium are very low. Both silicon and aluminium are very low. But the variations are like this. The variations are like this. That means for continental waters mean not all, most of them. Say for example, where you have bogs or peat, where all you put on all your dried leaves in a small depression and let the rainwater falls in it, the pH is much lower than 6. So it's much more lower than 6. So not all continental waters, but majority, say for example the river systems and the lakes, but the major body of water, There the pH is between 6 and 8. Although, as I told you, you can go up to 4 or even 3.5 for special types of rock. Possibly this is the whole range. This is the range for most of the waters. So if you do that, both silicon and aluminium have low solubility. That means it is difficult to dissolve silicon-aluminium framework. It is difficult to dissolve or break down minerals with silicon-aluminium frameworks. That's the first point. But in the range of most waters, aluminium has a much lower solubility than silicon. At the range of most continental waters, which are open to air, the aluminium solubility is much lower than compared to silica solubility. So, aluminium is the relatively immobile element, much more immobile compared to silicon. But if you go to the acidic range of the things, as you go to more acidic range, you can see the aluminium solubility increases both towards highly alkaline and both towards highly acidic environment. Aluminium becomes much more mobile. So you can understand that in the ocean water, aluminium would be more dissolved than in continental waters. Have you understood? In aluminium graph, if you are here or compared to here, the aluminium solubility is higher. So aluminium solubility in the ocean water is higher than in the continental waters. But the solubility of silicon is even higher. So the important point is, in the acidic environment, in the alkaline environment, both aluminium and silicon, the solubility increases dramatically. Although you don't have more alkaline rocks than this. But the silicon and aluminium both increases, but silicon has a higher solubility. But in the acidic environment, aluminium solubility increases, but silicon solubility is very low. So overall, then, for continental waters, if you take, then aluminium solubility is very low. Both solubilities are low, but aluminium has a lower solubility. So aluminium is not going to be dissolved in minerals very quickly. Right? So if silicon is much more dissolved from a rock where there is silicon-rich material, you will have voids and spaces. So you will create voids and spaces in the rock which exposes it to the atmosphere. Now, in general, for chemical weathering, if you have this type of situation where you have acidic material and ionic material, I think you still remember the Bowen's reaction series, where you had this Y-shaped situation, where you have olivine on the left-hand side, you had the incongruently produced material like olivine, orthoperoxine, amphibole, etc. And on the right side, you had plagioclase, the continuous series, and then you have quartz alkali feldspar. Normally at 25 degrees centigrade, 1 bar pressure, that means at the surface of the earth. The solubility, you see, as you go from higher temperature to lower temperature in Bowen's reaction series, similarly, the solubility decreases from high temperature to low temperature. So that means quartz is much more stable, which is at the bottom of the Bowen's reaction series, is much more stable than what is olivine, which is the high temperature molecule. So if you remember the Bowen's reaction series, then you know also how solubility works. If you have those minerals which are at the lower part of the Bowen's reaction series are the ones that are less soluble. And the ones, those are higher up, like olivine or calcic-rich plagioclase, these are more soluble. So, are more unstable. So, say for example, I will give you a reaction. Say for example, you know this Mg2SiO4 plus H2O reacts with H2O to produce MgOH whole twice plus H4SiO4. Now, if you need to balance this reaction, that should be a balanced reaction. So, if you have Mg2SiO4, which is olivine, reacts with water to produce this mineral, I don't think you know the name is brucite. So, you produce brucite, which is hydrated magnesium hydroxide, and you produce orthosilicic acid, H4SiO4. So, this orthosilicic acid now will be speciated into H3SiO4 into H2SiO4, 2 minus and 1 minus, plus H plus, or 2H plus. So once you have an olivine, it reacts with the water to produce brucite and gives you orthosilicic acid, and this breaks down into different speciations of H3SiO4 minus and H2SiO4 minus. And this is how it's related to the aluminium solubility curve. Similarly, this is, Mg2SiO4 is located at the top of the Bowen's reaction series on the left. So, olivine, for example, is one of the minerals which you almost always find, disintegrated or weathered or whatever it is. So then you have produced what you call as brucite. Say, for example, let me write another reaction, KAlSi3O8. I will just write it. This is a very classic reaction that if you have KAlSi3O8, you remember the name, orthoclase is another name, and then adularia is another name, and microclean is another name. So these are all polymorphs of KAlSi3O8. Whatever it is, you know orthoclase as the mineral. KAlSi3O8 is an important member of the more felsic igneous suits, as this we have discussed before. And so you have KAlSi3O8, it reacts with H2CO3, carbonic acid, plus 9CO2, and it produces this mineral. I will tell you the name. The name of this mineral is kaolinite. The name of the mineral is kaolinite. So, and then you produce again orthosilicic acid plus 2 potassium ions, and then 2HCO3 minus. Now these are dissolved. So is orthosilicic acid will dissolve depending upon the pH, as I told you before, and this is a mineral which will remain in suspension. It is a very stubborn mineral, kaolinite, which remains in suspension. So if you have KAlSi3O8, which is a mineral, plus H2CO3 and reacted by this system, which is 9CO2 plus H2CO3 in this proportion, if you react KLCO3, you produce kaolinite, which is a very stubborn aluminosilicate. It lies in suspension in the solid. But then you have 4H4SiO4, remember, and 2 plus and HCO3 minus. This could dissolve also and precipitate, or this would be carried out in solution. So there are materials that will be carried in suspension, there are materials that will be carried in solution, but what it does is it breaks down KAlSi3O8. So the more surfaces that you produce, the more reactions, the greater is the amount of reaction that goes to destroy the mineral and therefore destroy the rock. So these are the chemical reactions that occur in rocks. So if you have a rock and it's physically disintegrated by the different processes which we discussed, it decreases the size and it increases the surface area, and then they come in contact with the atmosphere and diverse reactions occur. And many of these reactions, they produce materials that are insoluble, like this, or brucite here like this, or materials that can be carried in solutions, materials that can be carried as suspensions. So you have a whole variety of material that are acting on the surface of the minerals. And as the surface becomes disintegrated, materials are taken out and new surfaces get exposed, and so you continuously break down the minerals. So essentially, if you take a rock from the Himalayas and trace it down the Ganges, so upstairs where you have the Himalayas, you essentially break them down. But as you take the materials downstream, they are continuously reacting with the atmosphere and with the rock and being disintegrated, and they become smaller and smaller in size. And when you go to the Bay of Bengal, it's almost a very fine sized material, very, very fine sized material. But you must remember one thing, that therefore, if you look at the Himalayas, you can study some aspect of the Himalaya by studying the sediments of the Bay of Bengal, isn't it? Because after all, the sediments of Bay of Bengal are deposited by the Ganges, and Ganges comes from the Himalayas. So some parts of the evolutionary history of the Himalayas can be studied. Also, the sedimentary sequences could be studied by studying sediments from the Bay of Bengal, the Gangetic Delta, or whatever else. Yeah. So there are also simple biological processes that help in breaking down rocks. So essentially, at the end of the weathering process, involving physical weathering, chemical weathering involving inorganic materials, or biological materials that react, and so materials are continuously being broken down and they are brought down to the surface. And now we go into what is called the erosion. How erosion occurs. Remember, erosion is the process by which this weathered material are brought down or moved away from their source of origin and is brought down to the source of deposition. So we now look at a little bit about how materials are transported in the river, for example. So fluvial deposits, those are deposited by the river. How are they deposited? How do they move? How do these different particles move along the river system? We are talking of let me draw the diagram first. Okay, what I give you is, before we go into, I think I will give you a small table. I will write it down. You write it down with me. Name of the particle, size range, loose sediment, and consolidated rock. I give you a table. Now this is a table that is used by sedimentologists the world over. The person who suggested this table are two people, two very famous people, Wooden and Wentworth. So this is called the Wooden-Wentworth scale. It is simplified and abridged a little bit. I've not given you the full table. It's not necessary at this stage. So first is the name of the particle, then is the size range, then you have a loose sediment, and then you have a consolidated rock. So from the loose sediment to the consolidated rock, what is the difference? Say for example, for a loose sediment, it is like this, loose sediments that are in contact. So what happens when you have a loose sediment on the surface, and when the loose sediment is progressively brought down as new sediments are piled one over the other, the oldest sediments is at the bottom and the youngest sediment is at the top. This we have studied before. And therefore what happens? There is pressure generated between the grains. So these are the pressure points. Can you see that? These are the pressure points. So what happens? There are three processes that happen. The first process is called compaction. So you compact the material. So when you compact the material, you remember you studied in school. What happens? When you compact the material, different particles, nearest neighbor particles in contact, they develop pressure solutions. Have you understood? So what happens when you have conceptual dissolution and then there is sometimes, so what happens from this stage to this stage, you then have you see, this is what is called all these pressure solutions, when you compact them, because of the compaction, they produce dissolution, and because of the dissolution, they get attached to one another over a longer spaces, and sometimes the material inside them, these are solutions that percolate through grain boundaries and they consolidate the rock. So this loose sediment is essentially this, and this is the consolidated sediment, which is essentially this. So in the consolidated sediment, you cannot take out simple grains. But when you go to the beach, for example, and take a salt, that's loose sediments. But when that sediment will be compacted because of the overlying pressure that is occurring on the sediment as newer and newer deposits is occurring, so the pressure points, they will solution. I think you know the term relegation, when you take two balls of ice and you press them with your hand, and after some time they are just linked. The two ice balls are linked together. So that's exactly what happens when you go from loose sediments to consolidated rock. Then this is called diagenesis. The conversion to this is called diagenesis. It's called diagenesis. Loose sediments to consolidated rock. This process is diagenesis, which involves compaction. Diagenesis involves compaction, pressure solution, and precipitation by replacement of the material. Sometimes some material is reacted by the solution and some precipitation occurs. So that also happens. So these are the processes: compaction, pressure solution, and precipitation through reaction are the three processes that are involved in diagenesis, which convert loose sediments to consolidated rocks. Right? So now, this is what is a rock. So, when you take the name of the particle is a boulder. It's larger than 256 millimeters, which is 25.6 centimeters. And then you have cobble, 64 to 256 millimeters, pebbles, 2 to 64 millimeters, sand, 1 by 16 to 2 millimeters. Now this is very, very crucial. Sand. 1 by 16 to 2 millimeters. And then you have silt, 1 by 16 to 256 millimeters. Remember all the diameter. And clay is less than 1 by 256 millimeters. So this is the name that is given to the particles, to individual particles. That is what the name is given to. And this is the size range that I have told you. And now what do you tell the loose sediments? This is not a particle. This is a cluster of sediments. This is an aggregate that you pick up with the hand. If it is this, more than 2 millimeters in size, it's called gravel. It's just called gravel. If you have 2 to 1 by 16 millimeter, it is called a sand. And if it is less than 1 by 16 to 1 by 56, it's called silt. And then you have clay. But remember, these words, these terms refer to the loose sediment aggregate of loose sediments. And this name is for individual sizes of the individual grains. And this is the name of sandstone, siltstone, claystone, conglomerate and breccia. These are names of the consolidated sedimentary rocks. So up till 2, these are, remember, this is not exactly wooden wetwork scale. It is an abbreviated, simplified version for you. Those of you who will go to higher classes will go into more classifications. The name is conglomerate and breccia. Conglomerate and breccia. Now, conglomerate is referred to something called rounded to sub-rounded aggregates, where the individual grains are rounded to sub-rounded. Whereas breccia, B-R-E-C-C-I-A, breccia, is the name given where individual grains are subangular to angular. Now, I will not go in details to it. I will ask you to read two aspects. One is called sphericity, and I will not explain this to you. Sphericity and roundness. Now, you have to read what is the difference between sphericity and roundness. Sphericity and roundness. What is the difference between that? Because I am talking rounded to sub-rounded. What does this mean, rounded to sub-rounded? And subangular to angular, what does it mean? So I leave this to you. You can read it from many sources. Sphericity and roundness of sediments you can find it from many websites. I will also send you a website from which you will be able to find out most of the things that are here. I will send you the website so that you can see it. But I leave it to you to find out sphericity and roundness. What is the difference? Is roundness synonymous with sphericity? Or vice versa, you can use them one or the other? Or is it not? But one thing, it has got something to do with a sphere. Yeah, but it is not the same. You have to read and find out. So when the individual grains are rounded to sub-rounded, you call it conglomerate. When it is subangular to angular, you call it breccia. For the size range larger than 2 millimeter diameter. But if you have a size range where you have 2 to 1 by 16 millimeter diameter, 2 to 1 by 16 kilometer diameter, 16 millimeter diameter, you call it sandstone. When the diameter of the individual grains are between 1 by 16 to 256, you call it a siltstone. And those which are lower than 1 by 256 millimeters, these are called claystone. So this is the definition that we will use. So boulders, so conglomerate, breccia, depending upon the roundness, sandstone, siltstone and claystone. These are all the sedimentary rocks based on the size of the clast. What is a clast? The clast is a fragment that is broken and transported from its place of weathering to its place of deposition. So any time you can trace it, that is called that is the name given to the rock. So you have to. This is the rock types that are named. So these are the classification of clasts. Clasts are individual grains, clasts are individual grains or that are rock fragments or different particles that are being transported from a site for weathering to the site of deposition at any point, and this is called clasts. Right. So now this is the Wooden-Wentworth scale classification, not the full thing, but reduced, abbreviated to make it very general at your stage. And remember, it is consolidated and loose sediments and rock. The processes that happen to it is called diagenesis, and diagenesis involves compaction, diagenesis involves dissolution, and diagenesis involves reaction with particles with the fluids that percolate through the boundaries of the grain, which helps to cement and compact the rock. Okay? Now, how are these particles? How are these particles transported? Now, I give you a diagram, and this we will make it as the last diagram. And this is the famous Hughes-Thrum diagram. This is the very famous Hughes-Thrum diagram. A scientist of great fame, and he gave us a diagram, and this is very, very instructive, and I will draw it here. There is something very interesting in this diagram. this we will make it as our subtopic for today, and then we will conclude. This famous scientist gave this diagram. If you plot Hull-Strom's diagram, you will get it all over the internet. And some places, if those of you who are interested in fluid mechanics, would also find parts of the derivations in many places. The result of this is, this has this diagram where the velocity varies from 0.1 to 1000 centimeters per second. Remember, here it's a log scale, so it's a log, each scale is a log scale. This is a log scale. And so here there are two curves essentially. One is the critical erosion velocity. That means if you have a particular material on a flat bed, and if you allow water to flow and you increase the speed of the water, at a particular speed sediments are lifted up. The lifted up means it's going to be eroded. So that's what is called the critical erosion velocity. And another graph which is the critical settling velocity. So you have a water with sediments and you draw the value and put the water to a flute, and depending upon the speed, materials will deposit. So you have what is called the critical settling velocity and the critical erosion velocity. So above this part, above this zone, you have erosion. Below this zone, here, this curve is transport in suspension. Below this curve, you have deposition of sediments. Above this curve, you have erosion of sediments. And this is the broad zone where sediments are transported as suspension. And this is the size range. Our important point here is, sand is 2 to 1 by 16 millimeter diameter sand. And so this is the sand size, and this is the erosion size. So you can see the erosion velocity increases for both larger and smaller. And smaller. The smaller you have, the erosion velocity increases. The larger you have, the erosion velocity increases. This is because the smaller particles tend to remain as aggregate through cohesion and adhesion. Remember? So you require higher and higher velocities to pick them up. Similarly, if the materials are large, especially boulders, for example, you need higher speeds to lift the boulders up and move it and erode it. Right? But if you look at this settling curve here, critical settling velocity, then you will see the settling velocity. Here you can see the settling velocity continuously increases with slight variations. It continuously increases. So the grains with larger sizes settle at higher speeds, and the materials at lower sizes settle at lower speeds. And in between you have a zone where materials are transported in suspension. Where materials are being transported in suspension. This is the zone where materials are being transported in substitution. Below this zone, you have deposition of material. Above it, you have erosion of material. But it is this velocity range and the size range along which materials are transported as in suspension. Okay, so I think in the next lecture, which will be the 27th lecture, we will elaborate a little bit more. So you must understand this, that for this grain size, the minimum velocity for erosion, roughly close to 10 centimeters per second, it is this sand which has the minimum critical erosion velocity. So sands are the ones that can be eroded with slower speeds. So if you can imagine a river system flowing down, you would require the smallest speeds that you have. You can move sand in suspension, but it will be very difficult to move the boulders or the finer grain material, which are the clay stone and here it will be clay stone and siltstones, it would be very difficult to even move them, and they would very, very high velocities. So once you have deposited clay or once you have deposited boulder, you require high speeds, but if you have saturated sand, it would require low speeds for being eroded and taken in suspension. And remember, the velocity required, it's very simple. The settling velocity is high for boulders and the settling velocity is very low for finer grained materials, which is understandable, which is also logical. Okay, then we stop here today. We will continue in the next lecture. Thank you.